if we got two shapes, let's draw two squares on the board. Okay? Actually, just two shapes. Are those two shapes similar?
No.
Okay, what does the word similar mean? It means the same. Okay, does it mean exactly the same or just alike? All right, are boys alike?
No.
Yes, okay. Boys are similar to each other. Are boys similar to girls?
No.
Some you may argue are, but okay, no. we're gonna go with the general rule that generally boys aren't similar to girls. Okay, and this is exactly the same thing with shapes. All right, we've got this idea that all squares are actually similar. All right, why are they similar?
They all have sides.
They all have four sides. I like it. All right, so that is similar to that. They all have four sides. That's a very good one. What is more than that?
All sides are parallel to each other.
All sides are parallel to each other. Cool. So squares all have two sets of corresponding parallel sides.
And perpendicular.
Sorry?
And perpendicular, 90 degree.
And there's 90-degree angles. Awesome. Okay, so we had one there. Sorry?
Equal.
All the sides are equal. Okay, so all in every single square that ever exists, okay, we always got four 90-degree angles, and all the sides are always exactly the same size as each other. All right? So it doesn't matter whether I take this square or this square, they actually are similar because they're very much alike. Okay, they're not exactly equal, but they're very much alike. All right? Same thing with triangles. All right? Triangles are as easy. All right? So what makes two triangles similar?
So all triangles equal up to 180 degrees.
Good, I like it, okay? That doesn't necessarily make two triangles similar though. And then we're going to have a look at what means a similar triangle versus two triangles that aren't similar. But let's start with the basics, okay? You said the very first thing you mentioned was squares. They have? Four sides. So triangles have?
Three sides.
Good, all right. So all triangles have three sides, guaranteed, okay? Otherwise it's not a triangle, all right? But we want to go a little step further than that, okay? Like you can get all humans, you could say, are similar. We're going to say boys are a little bit different to girls. We're getting different types of humans, okay? But boys are similar to boys and girls are similar to girls, all right? Triangles, this one's quite different to this one, all right? But how about these two? If my drawing was better, it would look a little bit better. But these two look quite similar, all right? What's different with this one and this one?
Size.
The size. This one is a bigger triangle than that one, okay? So that's the thing with similar triangles, okay? I want you to tell me a little bit about what these angles are doing.
Those are.
Yeah, we got something. Okay, they all add up to 180 degrees. Good, okay? That's very important with triangles. Another rule of triangles, okay? Triangles have three sides, and triangles, the angles always add up to 180 degrees, okay? But what I want to have a look is, again, specifically this idea of similarity. What connects this triangle to this triangle, okay? If I'm just taking this triangle, I'm making it a bigger version of itself, all right? What does it mean with the angles? Sorry? You guys, I think, on the same, sorry, but we got some here?
It will stay the same. Like
the angles are going to stay the same, exactly. So we have these two similar triangles where these angles are actually going to be exactly the same. So for any triangle that ever exists, I can make a rule, all right? And I can say two triangles are guaranteed similar, all right? And that's a mathematical terminology that we can now use if the angles are the same in the triangles. Okay? So if this angle is the same as that angle is the same as that angle, and that angle is the same as that angle. All right? But now there's a really cool property with triangles that comes along with that. Okay? Because the angles are the same, all right, we can learn something about these sides. All right? And you actually mentioned it in your card yesterday, so I'd like to just get it out of you a bit more. But what does it mean? All right? If we now have these similar triangles, what does it mean about the sides?
the sides are also equal to each other.
Okay,
Accurate.
good. I like the start, all right? I'm not going to say that sides are exactly equal, okay? Because, let me put this down. This side here, which corresponds to this side here,
yes.
This side's clearly a smaller side, all right? This side's the biggest side. We got something at the back.
The sides are equal, like the corresponding sides are equal in ratio.
You've got it. You've hammered it, exactly, okay? That's what's beautiful about this all right? The corresponding sides are equal in ratio. So, if, for example, that was 1, this side here, if we made it twice as big, is going to be 2, all right? And if this one here happens to be a number, all right? Think of a number for me.
5.
All right. But now, what if we don't know the number?
Number 8.
We put a variable, okay? Back to yesterday, what can variables be?
X.
Integers? Natural numbers? Can they be irrational numbers? Yeah, why not? Can they be rational numbers? So they can be real numbers. Right? This variable could actually be anything I like. Right? I don't know what it is, right? But guaranteed, if this is x and this is y, if this side here is twice as big as that side,
then the y should be twice smaller than the.
exactly, the y should be half of x. All right? So this guy is equal to 2 times y, or y is equal to a half x. All right, awesome. Exactly the same thing with the third side. All right, so that's the concept of these similar triangles, all right? And we're going to be talking about similar triangles a lot today because we've got a cool challenge that's coming up, all right? There's Rafiwa, all right? Where are you, Rafiwa? Yeah, all right. Fifi, okay, you're purple team, hey? There we go. Fixed you. Much better, all right. I tell you that you're given a pendulum, okay? And I'm going to set up a pendulum for you guys, and you're going to have this pendulum to test things out, all right? This is the challenge, essentially. I'm going to ask you to set up the pendulum, to drop it at a certain height, such that the ball will pass the bottom of its swing at exactly a certain velocity that I'm going to say, okay? Velocity is the same as the speed, but it has a direction. You've got it, okay? Because remember, velocity is a vector. So it has a magnitude, which is the speed it's traveling at, and it has a direction. It's going a specific way. So if I drop it from here, it's going to swing down in that direction and have a certain speed at the bottom of its swing, all right? So you're going to have to calculate for me in the next couple of lessons exactly how high you have to drop it from so that it swings down and reaches a certain velocity that I'm going to tell each team, okay, that they have to get at the bottom of its swing, all right? Now that potentially is quite a complicated thing that we have to work out. The first problem is how you're going to measure height, all right? Any ideas? A ruler. What if I'm going to ask you to lift it above the ruler?
What's on what in English?
Okay, so you can start to get measuring sticks maybe, okay? Somebody can estimate. It's not going to be very accurate. You're not going to get the best score at the bottom, all right? I'm also going to put a little constraint in this all, that you're not actually allowed to measure the vertical height, okay? You're only allowed to measure the horizontal distance, all right? So we're going to have to somehow map the horizontal distance to the vertical height so that you can let this ball go at the right height so that it swings down through the bit. And we're going to do a science lesson tomorrow discussing exactly why this energy is converted from height to speed. Okay, you'll all agree if you take a heavy object and you drop it here, it's going at no speed here, it's going quite fast when it hits your foot, all right? That's going to hurt, all right? When we start tackling this problem, it's going to be exactly the same understanding that we're trying to transfer into something that we drop over here and it swings into a velocity at the bottom. All right, you guys with me on the challenge? Cool, so now we've got to work with triangles to figure out exactly what we're doing, all right? This picture, I tried to explain how you're going to measure the speed of this thing, all right? Any ideas?
So, I don't know exactly how to explain it, but I know the concept of that thing in the background, that if you use a camera to put it down into slow speed and to catch the speed through that.
Cool. Okay, you did a pretty good job. Anyone else want to take a stab at it? All right. What would be the easiest way to do it? Sorry, we got some. Lizo.
What are we supposed to calculate?
The speed of the ball as it drops through the pendulum swing.
Do we know the initial height?
You do know the initial height.
So
You are going to get the initial height. So I'm going to tell you what speed I want it to be at.
Yeah.
You then go to calculate the height that you're going to take it to. You're going to let it go, and then you're going to tell me what speed it actually ended up to see if your calculation was correct.
So can we use the distance traveled and the time taken, or like the height that it...
Very, very good.
Okay. What he said, okay, you're gonna determine into the how can I explain it? The back thing, okay, you went so you went and you like painted or whatever certain type of colors and stripes onto this piece of thing that goes at the back of the ball that swings, okay, and then you're just going to record the ball swinging, and then you're gonna
Cool. Got some more ideas. Yeah.
I think basically the idea is to get we'll give the speed a variable because that's what we're trying to find.
Exactly.
So if we can find at least 3 points of which we know of,
Okay.
we can calculate all of those using a method like a formula. I'm not sure how you do math, but then with physics it makes
I like
sense.
it. I like it,
In
alright?
Afrikaans we work with afstand gedeeld deur spoed maal tyd.
Yeah, praat Engels for me.
Okay,
Sorry.
okay, it's a basic like formula where we use I don't even know what afstand is in English.
Afstand, spoed en tyd.
Yeah,
Guys,
that.
That's the.
good. Okay, formula thing. All right, it's good. We're gonna get to the formula thing. But remember a quote yesterday from Einstein, and we had, I think it was Liesel. You commented on keep everything or make everything as simple as possible, but no simpler. All right. My question to you guys: how could we measure the speed? All right. What about like those fancy things that the police use? All right, a ray gun. Would that be a good answer?
Oh my
That
God.
makes your lives really simple. You don't have to go into any of the maths, hey?
Yeah.
Okay? Unfortunately, we don't have one of those, okay? So we're going to have to make it a little bit more complicated. But yeah, sorry, we've got a question.
Oh, not a question.
Not a question.
Just an answer.
An answer, brilliant.
Okay, what is that thing with that is black and blue, the stripes?
Yeah,
No?
it's a checkered board.
Okay, we're gonna use that to measure the speed of the ball.
Exactly.
Using the camera.
Brilliant. All right. What's going to happen is you're going to use this camera, and you've all got great cameras on your cell phones. I've got a camera on my iPad, and we'll be able to take a relatively fast-framed video of this thing swinging past. All right. And we got it. All right. So at the bottom of the swing, as this thing passes in front of the board, you'll be able to take a frame and have a look at exactly what position it is. You'll be able to have a look at the next frame. Have a look at what position it is, and you know that if it traveled that distance in a certain time, you've got a velocity. All right? The problem with that is we've got a camera, okay, taking this picture of a ball and a screen sitting behind it. Okay? So can you see that from the camera's perspective, the ball is actually going to be a little bit bigger on the screen if we projected it onto one wall, all right? So we need to account for the fact that the camera is going to make a little bit of a bigger ball in our eyes. Okay, it'll make sense as soon as we hit the trigonometry now. So that is why, 2 reasons we're tackling trigonometry today. It's because we're trying to calculate what distance along the ground we need to hold the ball at, all right, to get it to the correct height, to get it to the correct velocity. And we're having a look at how much we need to make the ball a little bit smaller, times it by a ratio, to actually make this calculation correct and see if our calculations were right in real life. Okay, and we'll put this all to practice to see if it works.